In this video, I'm going to go over some basic Elasticsearch fundamentals and concepts that are going to be useful, especially for people who are beginning to delve into the Elasticsearch world. So for the longest time, data stores had been composed of SQL type data stores. We're talking about Postgres, MySQL, SQL Server, etc. But in the last couple of years, there's been an uptick in the number of NoSQL type databases such as Elasticsearch, MongoDB, etc. So in this tutorial, I'm going to go over and I'm going to do an overview of the Elasticsearch data store, which stores documents as NoSQL in the form of JSON documents. Elasticsearch itself is focused on providing search functionality to clients. Indeed, it does store documents, but its main focus is on providing search functionality and also some analytics functionality to documents. So think about a website where you want to have some search functionality. Sure, those SQL data stores could do this if you could use select statements. However, those were limited to like keywords. So you could only search for select all users where the name is John, or if you wanted to go further than that, you could use like a like statement, which did some light search actions for you. However, the Elasticsearch, it goes over and above that when it comes to searching. You could search by synonyms, you could search by partial phrases, you could search by partial strings, you could search by geospatial coordinates. So there's a whole range of functionality that Elasticsearch provides that other SQL providers did not provide. What exactly is Elasticsearch? Elasticsearch is the distributed search and analytics engine at the heart of the Elastic Stack. Logstash and Beats are also other components of the Elastic Stack. Logstash is an extract, transform, and loading tool, which means that it is able to fetch documents or data from one data source, perform some transformations on it. For instance, if you want to change the date from a European format to an American format, and then load that data into Elasticsearch. Kibana is a tool that enables us to explore, visualize, and share insights into our data and manage and monitor the stack. In this tutorial, I'm just going to focus on Elasticsearch, which is where the indexing, search, and analysis magic happens. Elasticsearch provides near real-time search and analytics for all data types. So what does near real-time mean? This means that when a document is stored in Elasticsearch, it is available for search within 1 second. This is quite impressive considering that Elasticsearch is distributed. Therefore, when you store a document, it has to be propagated to all the nodes. And when someone performs a search, that request can hit any node to retrieve the document. So that document has to be in all of the nodes in 1 second. In addition to Elasticsearch being near real time and fast, another way it shines is because of its full text search feature. In the SQL world, when we're doing a search, we mostly match on the keyword. So for example, we'll search for a document or rows where a certain criteria matches. So for example, we'll search for all customers where the last name equals Smith. If you misspell Smith, nothing's going to show up. Well, if you use a like statement in SQL, it might show up. If you say search for all customers where last name like, SMIT, that will probably bring back the documents you want. But for the most part in SQL, we only search for keyword matches. In Elasticsearch, however, this is not the case. When you do a search, it's going to perform a full text search, meaning a lot of things can match even though they do not match the search term. So for example, if you search for Smith, you search for documents where the last name is Smith, but you misspell it. Because of the way Elasticsearch works, it's going to search for documents where the term kind of matches Smith. It's going to perform a score. It's going to score all the documents and it's going to rank them based on the relevance or what it thinks is relevant and return those documents to the client. So even though you misspelled Smith, Elasticsearch can potentially return to you documents where Smith actually exists and therefore you're able to get the documents you want. This is not always the case, so it depends on how you have indexed the documents. But for the most part, this is where Elasticsearch shines because it does not do or it does do keyword or exact matches, but for the most part, if you are looking for documents that are relevant to what you're searching for, Elasticsearch is going to return them to you based off of a score. I think that's where the difference lies because in Elasticsearch, you can either search for the exact keyword a la SQL, where you just want to match the exact word, or you can search for a term, but then you're expecting documents that somewhat match the term or are relevant to your search. That's where the big difference lies. So if you have an application How can Elasticsearch help you? With Elasticsearch, you can add search functionality to your applications. For example, if you have a website, an e-commerce website or something, you can add a search box to it and then use Elasticsearch on the back end to find anything that your clients search for or your consumers or the end user search for. You can also store and analyze logs, metrics, and security event data. So Elasticsearch is big as well on storing logs, and those logs can be analyzed and queried for using Kibana, which is part of the Elastic stack. You can also use machine learning to automatically model the behavior of your data in real time. You can automate business workflows using Elasticsearch as a storage engine. You can manage, integrate, and analyze spatial information using Elasticsearch as a geographic information system. And you can store and process genetic data using Elasticsearch as a bioinformatics research tool. The way clients can interact with Elasticsearch is via a REST API that Elasticsearch provides. This is extremely convenient because REST APIs are commonplace in the web development world. So by Elasticsearch providing access to the backend or the libraries using the REST API, it makes it easy for developers to integrate the solutions with Elasticsearch. So Elasticsearch provides REST APIs for indexing, which means storing documents into Elasticsearch and then also searching for documents using those same REST APIs. And the REST APIs are very rich. They have a lot of functionality, so you can do pretty much anything you want that Elasticsearch exposes via the REST APIs. So let's talk about how data gets into Elasticsearch. When a document is stored, it is indexed and fully searchable. What that indexing means is just it means storage. A document is received from the REST API that Elasticsearch exposes, and it is stored. Now, documents are modeled as JSON documents. So in SQL, we have a table that has rows. In Elasticsearch, you have an index that has JSON documents, and the JSON documents have fields. So the fields have values. So you have a key and a value. So for example, you could have a document that has, let's say, it's a person document and it has a field named first name and the value is Jim, and it has a field named last name and the value is Smith. So that's what they mean by JSON documents. So as opposed to having a SQL row where it would have a column named first name with the value Jim and another column named last name with the value Smith. So when documents are saved in Elasticsearch, they are stored in indices, which, as I mentioned before, makes them searchable in near real time. So prior to Elasticsearch 8.0.0, the Elasticsearch document structure consisted of indexes, types, and documents. So an index was supposed to represent a database in the SQL world. A type was supposed to represent a table in the SQL world, and a document is supposed to represent a row in the SQL world. But as of version 8.0.0, types are deprecated. So now we just have indices and the documents. When you save a document in an index, it is saved as an inverted index, which facilitates fast searches. So an inverted index is essentially you take the document that you are saving, break it up into all the terms. Each term points to the document that the term exists in. And I'll show an example of this in the next slide. Elasticsearch also has the ability to be schemaless, which means that documents can be indexed without explicitly specifying how to handle every field in that document. When dynamic mapping is enabled, Elasticsearch will automatically detect the field in your document and try and assign it a data type based on what the field looks like. So for example, if you have a number or numeric field in your document, Elasticsearch will intelligently try and assign it maybe to a long or integer depending on what the field is. So that is how schemaless works. On the other hand, you can have schemaful, which is basically how to handle structured data. In this case, dynamic data will be rejected. And the way you do this, you have a setting in your Elasticsearch index that says dynamic mapping is set to strict. So if it's set to strict, only the fields that are defined in the mapping that you provide when you create the index are going to be allowed. If there's an extra field that's not part of the mapping, an exception will be thrown. The benefit of having your own mappings or having a strict mapping is that you can distinguish between full text string fields and exact value string fields. You can perform language specific text analysis. So if you have English versus Korean versus Arabic, you can specify that in your mapping and you'll be able to handle that appropriately as opposed to having Elasticsearch try and figure out what language that is and apply the mapping for that. You can also optimize fields for partial matching. You can use custom date formats because by default, Elasticsearch is just going to apply the date format that it thinks makes sense. And then you can also use data types such as geopoint and geoshape that cannot automatically be detected. Sometimes it's useful to index the same field in different ways for different purposes. So, for example, let's say we have a document called article that has a title field and a content field. We might want to store the or index the title field in two different ways. We might want to index it as the entire title field without breaking it down, which would be a keyword data type. And then we might also want to index it as a text data type, which means that it's broken down and analyzed based off of the analyzers that we specify in Elasticsearch. So this is useful in the sense that now we can use that same document that we indexed for various purposes. So if you want to do like sorting and aggregation, which typically depend on keywords or the exact match, now we can use the title field that we index as a keyword to do the sorting and aggregation. However, if you want to do like a full text search where we want to match on partial words in the title or words that kind of match the title based off of what Elasticsearch does on the scoring, then we can also do that. So this is where Elasticsearch really shines, where we can have the same field, but we can index it or store it in different ways or different formats so that we can use it for different purposes. So here's an example of two documents that we stored in Elasticsearch. The first document has a name of Jim James, age 77, vaccinated, false. Second document is James J, age 55, vaccinated, true. Now, these are the documents that are stored in Elasticsearch. When you're doing Elasticsearch indexing, you can either store them one by one or you can do bulk indexing. Whatever the case, that's not important here. What I want to show is what's going on, especially in this name field. This is how the documents are stored in the inverted index in Elasticsearch. We have the term James, which shows up two times in our index. So if you come back here, we see James, there's James 1 here, James 1, another James here in the second document. So those are two frequencies. It happens twice. And it shows up in documents 1 and 2. Come back here, ID here is 1, ID here is 2. So that's how that shows up. Then you have J, which is the last name of James J in ID 2. And the other thing that this highlights is that in the inverted index, the terms are ordered alphabetically in ascending order. So it goes from A, B, C, D to Z. So here JAM comes before JAY. That's why we have it second. And then it only appears once and it appears in document 2. Then you have Jim, which appears once as well, and in document 1. So that's how the inverted index looks like. It's essentially a sorted index that shows the frequency of the words and the documents in which the words appears. So here I want to talk about how Elasticsearch does its search and analysis. So Elasticsearch, as mentioned before, supports structured, full search, and complex queries. And what that means is that if you're talking about structured queries, we're talking about keywords queries. So with Elasticsearch, you can actually perform the same queries as you did in SQL, where you're just searching for keyword and it will return what you want. And this is mostly done through filters. So you can search for, get me all customers whose age is greater than 25, and Elasticsearch will do that for you. You can also do full search rates, like get me all customers whose name is Jim or Jimmy, and whose profession is dev. And Elasticsearch is going to find you all people named perhaps James or Jimmy, and then whose profession is dev or developer or something along those lines that is matching what Elasticsearch has or how it's configured. So it's not going to be an exact match, but it's going to do a query and figure out do a performance score on all the documents that match and then return all the documents that are relevant to you. So that's what the full search does. And then you can combine the two of those. You can combine the structured, the keyword, and the partial or the full search, where it's like, okay, give me all the documents that match exactly what I want, and then also kind of partially match or are relevant to what I'm searching here. And that's where the complexity comes in. So you can do either of them in isolation, or you can combine the two, which is very powerful in Elasticsearch. Another cool functionality that Elasticsearch has is that it can perform geospatial queries. So think about, any app that you've used where it has asked you or it has fetched certain results based off of your location. So this is similar to like dating apps, to food delivery apps, to anything where it's like, hey, what's your location? And okay, I'll find you results within an X mile radius, within 5 miles radius, 10 miles radius. Elasticsearch is very, very competent in doing this. So Elasticsearch is a very robust solution when it comes to geospatial queries. In addition to doing geospatial queries, Elasticsearch can also search for individual terms, phrase searches. So if you want to search for a phrase and have Elasticsearch score that and return relevant documents to you, you can do that as opposed to doing keyword searches. You can do similarity searches. So these are things like synonyms. So you can search for one word, and then if a synonym matches that in Elasticsearch, it's going to return the document. You can do prefix searches. So if something matches a prefix, Elasticsearch will return the document. And we can also do autocomplete suggestions. When you're performing search requests against Elasticsearch, you need to use the Elasticsearch's query domain specific language, which is a JSON based language. So all the requests you send to Elasticsearch should be JSON based. So if you're using an Elasticsearch client SDK, for example, Java or Python, when you write that code in those languages, it's going to transform that into JSON and send it to Elasticsearch. If you're using something like Postman, you have to define the request in JSON and send it to Elasticsearch. You can also construct SQL style queries to search for and aggregate data natively inside Elasticsearch using JDBC and ODBC drivers. In addition to doing search, Elasticsearch can also do analyzation of your data, so it can analyze your data. Elasticsearch applications enable you to build complex summaries of your data and gain insight into key metrics, patterns, and trends. So instead of just finding the proverbial needle in the haystack, aggregations can enable you to answer questions like how many needles are in the haystack? What is the average length of the needles? What is the median length of the needles broken down by manufacturer? How many needles were added to the haystack in each of the last 6 months? You can also use aggregation to answer more subtle questions such as what are your most popular needle manufacturers? Are there any unusual or anomalous clumps of needles? Because aggregations leverage the same data structures used for search, they're also very fast. This enables you to analyze and visualize your data in real time. Your reports and dashboards update as your data changes, so you can take action based on the latest information. Not only that, aggregations operate alongside search requests. You can search documents, you can filter results, and perform analytics at the same time on the same data in a single request. And because aggregations are calculated in the context of a particular search, you're not just displaying a count of all size 70 needles. You're displaying a count of all the size 70 needles that match the user's search criteria. Here I'm showing some documents that I have in a demo index. So the document consists of a brand field, a color field, a waist field, and a length field. So each document just represents a brand of pants. And I have 10 documents as shown here, total value 10. And I have 6 Levi documents, and I have 4 Evisu documents of different colors. So what I want to show here is how search can be used to gather aggregations in Elasticsearch. So this is a generic, just get all documents in the index. Now, here, let me get rid of this. So here we have the aggregation query. So just saying aggregate all the documents in this index and group them by the color. So let's see what that does. So I run that, and now we see that it still performs a search, right? It will give us the search results, and then if we go all the way at the bottom, we'll see the aggregations. So here we have 5 red pants, we have 3 blue pants, and we have 2 black pants. And if we go through this, we'll be able to verify that we do have 2 black pants, 3 blue, and 5 red. So I'll just do the ones for the blue. So blue, let's see, 1, 2, and 3. So the aggregation is correct. All right. So now let's say we want to just filter. We don't want to show the Evisu. We don't do any aggregates for the Evisu pants. So we'll come and say we'll add this query. This is a filter that filters out or only shows us Levi genes. And in addition to that, so it will fetch the Levi genes and then perform the aggregation on those search results. So let's run this and see. And now here we only have 6 documents, which coincides with the number of Levi gene documents here in this index. So if we count these documents, we'll see there's only 6 of them. So 1, 2, 3, 4, 5, 6. And then in the aggregations, again, these add up to 6 at the same time. So 3 plus 2 plus 1. So what we did here, we filtered out and said we don't want to do aggregations on the entire documents in the index. We just want to filter out and only do aggregations on the documents whose brand is Levi's. So this can be very, very powerful. This is just a very simple example of how Elasticsearch can be used for aggregations. But the idea here is that you can search and then perform aggregations. You can perform sub-aggregations. You can do so many things with Elasticsearch aggregations, and this is just scratching the surface. Because Elasticsearch is distributed in nature, it can scale easily and is also quite resilient. Elasticsearch runs in a cluster, which is essentially just a collection or group of servers that are connected to each other. And each server stores data that is in an index, and that index is broken down into shards. So the shards are spread out across the nodes, and that means that if one node goes down, your data is still available. In addition, if you want to increase your storage capacity, you can add more nodes, and Elasticsearch will automatically spread or write your documents into those new nodes. And then this also offers another benefit that because you're increasing the number of replicas, because as you add more nodes, if you have your replica settings, they're going to be replicated into the new nodes. So that means that you'll have increased capacity to serve read requests like searching or retrieving a document. So what is a shard? You can think of a shard as a self-contained search engine that indexes and handles queries for a subset of data in an Elasticsearch cluster. So a shard is the smallest possible unit of storage in Elasticsearch, and each document that you store is associated with one primary shard. And if you have a replica, or if you have the replica settings, you will also have a replica shard, which is basically a copy of the data from your primary shard. And these shards, as mentioned earlier, are spread across the nodes, and that's what provides scalability and availability. The way it works is that documents are written to primary shards, and then they're copied to replica shards. Reads can be done on both primary and secondary shards. So that's why when you add more nodes and a search request comes in, it can either go to the primary shard or the secondary shard, which is a difference now between the writes and the reads, because writes are only written to the primary shards. So you can be bottlenecked by the number of primary shards you have. But when it comes to reads, they're spread across both the primary and secondary shards. Also, the number of primary shards cannot be modified after index creation. So that means you have to figure out using some either type of experiment, or perhaps you just know how much data you're going to have and you can approximate, and then you can figure out the number of primary shards that you are going to assign to your index. Elasticsearch has an article about this in the documentation. And then also replicas can be modified without any downtime. What that means is that we can change the number of replica shards at any time, as opposed to the primary shards where you cannot modify the number of primary shards. And when we change the number of replica shards, Elasticsearch is going to apply those changes without interrupting any indexing or query operations. Here we have an Elasticsearch cluster that has 3 nodes, node 1, 2, and 3. And it consists of one index, which has 2 primary shards, P1 and P2, and 2 replicas, R1 on node 2 and 3, and then R2 on node 1 and 3. One thing to notice here is that each node has a complete data set, because in Elasticsearch, data is stored in the shard. So the data that's on P1 is not the same as the data in R2, but the data in P1 is the same as the data in R1, and the data in R2 is the same as the data in P2, because the replicas are just copies of the primary shards. For example, if node 2 goes down, what will happen is now I'm missing the primary shard 2 here. And so Elasticsearch is going to come here and promote R2 to a primary shard. That way we can still receive write requests, because write requests are only done by the primary shard. So any write requests that were supposed to be done on this P2 that went down will now be redirected here. And that way the resilience of Elasticsearch comes into play because now we're not blocked by having this node being available. We can just resume our operations because our write operations because Elasticsearch will promote this R2 to P2. Now, in terms of scalability, the more nodes you add here, the more Elasticsearch is going to spread out the shards and try and figure out an even way of spreading out the shards as you add more nodes. So Elasticsearch provides a lot of good functionality to make your application scalable and available.